Hello, my name is Alan Huang and I am the Product Manager for Image Acquisition Toolbox here at the MathWorks. I'd like to welcome you to the Image Acquisition and Processing using GigE Vision Cameras webinar. There's quite a bit of information and demos I'd like to show you over the next 45 minutes, and I'm very excited to highlight some of the new features that's been released for Image Acquisition Toolbox. So let's go ahead and begin by looking over the agenda. I'd like to start us off by taking a step back and looking at all the places that image acquisition and processing is used. I find it's useful to frame our conversation by considering the types of requirements and, more importantly, challenges that we have to work with. Next, I'd like to give a quick overview of MATLAB and our image and video processing products and how they can help us work with these types of problems and challenges. As I mentioned before, there are a number of new features that I'd like to highlight for Image Acquisition Toolbox, in particular, features relating to GigE Vision. So we'll have a section overviewing these updates. Now, I'd like to spend a good amount of time in MATLAB so I can show you how you can use these tools in action. I'll sprinkle some demos throughout the webinar, but our main example will be a demo detecting fingertips, which poses a pretty interesting image processing problem. So with that, if there are any questions, we'll have a question and answer session at the end of the webinar. But if you have any questions in the meantime, feel free to type them in during the webinar. It'll basically queue up and I can collect them together and go through them one by one at the end. Okay, so with that, let's go ahead and get started. So where is image acquisition and processing used? Here, I've listed a number of industries that make use of grabbing image and video data from cameras and frame grabbers and using it in some way to make some sort of decision. In the aerospace and defense industry, we might be looking at cameras mounted on a UAV, or unmanned aerial vehicle, and it's trying to track some objects moving around a landscape. We could be using infrared, visible, or even a fusion of the two. In some industrial applications, we might be looking at silicon wafers or solar panels and trying to find flaws to catch them before they move on to further processing. And to highlight one more, in the automotive industry, I think we've already been seeing image acquisition make widespread impact on safety systems, backup cameras, lane detection, and internal-facing cameras for airbag deployment. And all these industries, although different, have very common image and video processing tasks. For example, we might need to segment an object, characterize it, and input its position to a tracking algorithm. And that process can occur regardless of the nature of the imagery itself. And so the types of processing is the same, and as a result we see a very common set of challenges. And here I've listed some common challenges when working with image acquisition and processing problems. And the first one is really the core issue here. How do we design an algorithm to be robust from just a handful of test cases? When designing an imaging system, we might start with just a handful of these images, but once we deploy an algorithm to real-world conditions, it's likely that lighting, different backgrounds, and foreground objects may cause the algorithm to fail. So we need to be able to test an algorithm early on with a lot of test cases before moving it to deployment where it's more expensive to make fixes. And that leads us to a second challenge. There are a lot of software packages available to connect to cameras and import data. But with that, it's difficult to connect that data to your image processing environment. Manual transfer of data can be quite cumbersome, especially when you want to test many cases. So ideally, it would be better to have a workflow that automates this process, so it's easy to test live data on your imaging system. And this workflow is what we call the technical computing workflow, and it demonstrates how you can develop an algorithm using MATLAB. The first stage is accessing data, whether it be from files or, in our case, cameras. And you can bring that data directly into this exploration and discovery stage. Here we try out different algorithms, make changes to produce the most robust algorithm possible. Lastly, we share the result in some way, whether it be through visualizations or actually taking the code and deploying it to PCs or embedded hardware like DSPs. An important process in this whole workflow is this circular arrow, the ability to automate this process. So over the next couple slides, I'd like to highlight the image and video processing products that fit into this workflow. With that, we can then dive into MATLAB and start looking at how to use the software through several examples. And for those who haven't seen MATLAB before, I'll be sure to give a quick highlight of the environment so you're familiar with it in the demos. But there are a lot of videos available on our website that give great instructions on how to use it. So first and foremost, we have Image Acquisition Toolbox, which provides access to cameras and frame grabbers. The toolbox enables you to bring images and video directly into MATLAB and provides both the programmatic and graphical interface to the functionality. So with the toolbox, you can perform tasks like background acquisition, synchronization of multiple devices. And especially with functional access, you can easily automate the process. So this is addressing that second concern in our challenges. In our demos, we'll make use of this, but also show you how you can use subsequent image and video processing products to address our other main concerns, like creating a robust algorithm. And that brings us to Image Processing Toolbox, which you can use to develop algorithms. Once you've acquired the data using Image Acquisition Toolbox, you can use the Image Processing Toolbox to analyze and process the data. Here I've listed the major features in the toolbox and the areas it gives you functionality. In our demos, we'll focus our efforts mainly on image analysis, but I did want to list out other capabilities. But unfortunately, due to the time constraints, we won't have time to go into all these other portions. But there are a number of demos and recorded webinars and recorded videos on our website that go through these areas in more depth. So if you're interested in learning more, I'd recommend checking those out. Now lastly, we have Computer Vision System Toolbox, which is also used to analyze and process video data streamed from cameras and frame grabbers. The System Toolbox provides extra functionality that's geared more for video processing and computer vision. It consists of a collection of functions and what we call system objects. System objects is a technology that provides infrastructure for video processing. For example, these objects would automatically handle buffering, indexing, and state management. So like Image Processing Toolbox, we'll highlight some of the tools in our demos, but unfortunately, we won't have time to go through the entire product. But again, there are many demos and webinars available on our website that go through Computer Vision System Toolbox in more detail. So feel free to check them out. Okay, so with that introduction, we've essentially explored the idea of where image acquisition and processing is used and what kind of MathWorks products are available to solve the associated challenges. So I'd like to move us towards the more hands-on portion of our webinar. We'll be looking at 3 different demos today, each getting more in depth with the products. Here I just want to give us a quick intro to Image Acquisition Toolbox using the graphical tool called iMac Tool. So with iMac Tool, we'll see how we can set up some properties, like these listed here, and with that, let's go ahead and jump into MATLAB. So this is the MATLAB desktop. For those who are not familiar with the environment, let me give you a quick overview of all these different windows and how you can use them to work with your data. And the setup of the MATLAB desktop is completely configurable, so this might look a little different than what you see on your computer, and this is generally how I tend to arrange my windows. On the lower left, I have the command window, and this is where you can do things like create variables, call scripts and functions, and interact with your data. So for example, I create a variable A and B and add them together. Now one of my favorite things about MATLAB is how you can work with matrices. It's very easy to do things like index into them using colon operators and logical indexing. So as an example, let's create a sample image using this function called magic, and I'll just create a 5 by 5 matrix. What we can do to index into it is use the colon operator, 1 colon 2, and say 4 colon 5. What this does, MATLAB will go through and look at rows 1 and 2, columns 4 and 5, and grab out this top right corner for us and pass it back. So it's very easy to go ahead and grab a particular portion. To do something a little bit more complex, we can create a new variable index and look at, say, values greater than 10. What this has done is created a new 5 by 5 matrix of logical values, where there's a value 1 whenever matrix I was greater than 10. What we can use this for is logical indexing into the original variable I. So anytime we see a value 1, we can set the original variable I to some new value, let's say 0. Now this is extremely useful when we start doing things like masking and segmentation. And if you tried to do something like this in C, we'd require multiple for loops, and it's generally more difficult to implement than this line of code. So this is one of the real benefits that MATLAB provides when working with matrices. And since images are essentially matrices, there's a lot of benefit to doing image processing within MATLAB. So on the right hand side here we have the MATLAB documentation, and this is where you can find information about all the functions in MATLAB and the toolboxes, setup information, as well as some tips on programming styles. So it's a great place to get some extra information. Over here is the MATLAB editor. We'll come back to this in the next 2 demos, so let's just leave this for now. We'll come back to it. On the top left, I've arranged the workspace and current folder. The current folder is where you can look at all the files that's in the current directory. Let's say there were some mat files, you can click on that and take a look at its contents here in the details pane. With the workspace, we can see all the variables that we've created up until now, the sizes, and their classes. You could also look at some other statistics as well. Now let's go ahead and dive into iMac Tool. You can access it by typing iMac Tool in the command prompt, or you can go to the MATLAB Start and navigate over to Image Acquisition and click on the Image Acquisition tool. Now this graphical interface has a number of windows itself, and I'll go through them one by one. On the left-hand side, we have basically our hardware browser. Currently, I have two cameras hooked up to my laptop, and we can see all the different modes that are provided for each one here. Now, here's my USB camera and our GigE Vision camera. So we're going to work with this one in the next two demos. Let's concentrate on this USB camera. When I select this over here, our information pane is updated with some data on the device, the resolution, as well as some logging and trigger types. I think the easiest way to learn about these is to go through the acquisition parameters pane here and these different tabs. On the furthest right, we have region of interest. So you can select out a particular portion of your frame. As you generally select smaller portions, you can raise your frame rate. Over here in the triggering, we basically have two modes, immediate and manual. So these are the two modes for this particular camera. For other ones, you might see another one called hardware triggering. I'll cover that in a little bit. Now immediate is basically free running. So if I click start acquisition, we just immediately start grabbing some frames. Under manual, this is software triggering. So let's say we had an image processing algorithm and some logic to indicate when to start acquiring data from our camera. This is the triggering mode that you want to use to perform something like that. In this graphical interface, manual basically enables this button here, which will allow us to manually trigger it by mouse clicking. Now over here in logging, when you log data, by default is loaded into memory. But if you need to grab multiple frames over a long period of time, you might want to put it to disk. And we'll do that in our next demo actually. Over here in device properties is probably where you spend most of your time. This is where you can access things like backlight compensation, brightness mode, contrast, exposure, and so forth. Now this is going to change with the camera that you select. This is just what is shown for this particular USB camera. And under general here, we can set the number of frames you want to grab per trigger. Right now it's just set to default. So let's go ahead and run an example. Let's say I want to trigger 3 times. And let's grab 10 frames per trigger. So let's just set that to 10. What I'll do is start previewing. So this is a view of Apple Hill 3, one of the main buildings on the MathWorks campus. What I can do is hit start acquisition. We'll see that the trigger and stop acquisition buttons have been enabled. And so I'll manually trigger this one. Say our image processing algorithm, the logic determines, okay, let's start triggering now. We click it, it grabs 10 frames at the frame rate that we've specified, and we can go ahead and trigger the next 2. When this is done, it'll collect up some of those sample frames and display them in a montage. It doesn't display all 30 because that would be too many images to look at. So it selects a particular portion of them to give us an overview of what we've captured. Now there's one more window I'd like to discuss, and that's the session log. Now all the actions we've done to set up our hardware, set up the acquisition parameters, has been recorded here in the session log. So as I mentioned before, Image Acquisition Toolbox gives you both a graphical interface and a programmatic interface to all the features. And so this is the MATLAB equivalent to all the actions we've done inside this tool. So let's say we wanted to automate this process of configuring the camera and grabbing data. You can copy this, put it into a MATLAB script or function, and go forward with that. And so with that little example, let's go ahead and jump back into the slides. We'll go ahead and delete the frames that we acquired and jump back into PowerPoint. So from this demo, we got a sneak peek at hardware triggering, and I wanted to cover a topic that's pretty related to that, and that's the image acquisition engine. The toolbox was designed so the engine runs on a separate process than MATLAB, and this enables features like high-speed acquisition, asynchronous acquisition, and multi-device synchronization. So going back to hardware triggering, some cameras allow you to hook in an external signal so that you can time it with other devices. And so the toolbox supports this type of workflow. With the particular USB camera that I was using, that option wasn't available to you. But if that's something you're looking for, the toolbox does support it. Now the diagram below here shows the relation between MATLAB and the acquisition engine. You can interact with the toolbox in MATLAB either in iMac Tool like we just saw in the previous demo or using the functional interface. And the information is passed along to the engine, which in turn talks to cameras and frame grabbers. And since it runs on that separate process, the data is written to a buffer as fast as the hardware will allow. Now we'll take a look at 2 modes in the next 2 demos where we store all the data and post-process as well as process in the loop. So up until now, we've taken a high-level view of what Image Acquisition Toolbox is. Now I'd like to bring everyone up to speed with what is new in the toolbox. In R2010B, Image Acquisition Toolbox received several updates. First and foremost, the ability to communicate with GigE Vision cameras was added. Now, this is an important addition as it opens up a large number of cameras for users to work with in their applications. I'll dive more into that in a further slide. Now, additional features in Toolbox extend support to Linux and Macintosh. I have listed here some various interfaces supported, such as DCAM, FireWire, and common webcam interfaces like Video for Linux 2 and QuickTime. So I know many users make use of other types of cameras in their applications. And although we are highlighting GigE Vision cameras in the next two demos, you can switch them out with other types of cameras as needed. So let's go ahead and dive into GigE Vision in more depth. For those who aren't familiar with GigE Vision, it's an interface standard maintained by the AIA for sending images and video over Ethernet. Now this is great since most computers already have Ethernet cards and you don't need specialized hardware to work with these cameras. GigE Vision has very high data transfer rates, around 1000 megabits per second, and data can be spent over long distances. Also, as you look into working with GigE Vision cameras, there are a number of ways you can connect to these cameras, using either routers and hubs and dual-port Ethernet cards. Let's go ahead and dive into an example working with the GigE Vision camera I have hooked up to my computer. And in this demo, I'd like to highlight how Image Acquisition Toolbox operates on a separate process, enabling us to capture at fast frame rates. So let's have a little fun. I've set up a GigE Vision camera to look at this printout of this regularly spaced 1-inch lines. What I'm going to do is shoot a rubber band through the frame and post-process the clip to calculate its speed. I'll then create a visualization to see how it moved through the frame. So let's go ahead and jump back into MATLAB and use the iMac tool to set up this experiment. Okay, so let's go ahead and jump into MATLAB. The first thing I'm going to do is open up iMac tool. And rather than focusing on the webcam that we used in the previous example, let's go ahead and focus our attention on the GigE Vision camera up here. Now this is an Allied Vision Technologies GigE Vision camera. It's called the Manta. And we can see that there are many modes for us to choose from. What I'm going to choose here is Mono 8. And we need to first set up the camera with the acquisition parameters down here. So the first tab I'll take a look at is Device Properties. And we immediately notice that the frame rate is around 17. So that probably won't be high enough to capture the rubber band as it flies through the field of view. So to increase this, one way you can go about it is by changing the size of the frame. Over here in region of interest, we see that the size of the frame is fairly large, about 1300 by 1000. So one way we can turn this down is to use binning. What I'll do is set this to 8, and this will basically take 1 out of every 8 pixels and effectively reduce the size of the frame. So if I click Start Preview right now, we should get some view of that piece of paper. Let me focus it for us. And if I go over to region of interest, we see that it's become much smaller than 1300 by 1000. In addition, the maximum frame rate is now around 59. So what I can do is set this to 59 and it will automatically update for me. So let's go ahead and first set up some of the logging. So right now we were logging to memory. Let's go ahead and switch this to disk since we want to capture multiple frames. Okay, so we're going to set this to rubberband_demo.avi. Okay, and we need to set the frame rate. So let's set that to 59. So under the General tab, we need to set how many frames you want to capture in this trigger. Now, if we recall, the default should be a single trigger, which we will immediately start when we hit this Start Acquisition button. So once I hit this, we'll need to specify how many frames we want to capture. So let's go ahead and just enter 1000 frames. That will give us over 10 seconds of data in order to shoot the rubber band through the frame and capture it. So I'll go ahead and start acquisition and shoot the rubber band through the field of view. Okay, so I shot the rubber band through. Let's go ahead and see if we can review our data and find that rubber band. So what I'm going to do is go ahead and minimize this. We should see our file over here. So I'll go ahead and clear out this screen. And so I'll use this function called mplay to watch this video. all I need to do is pass the name of the file to it, which is rubberbanddemo.avi. Okay, and we can see that it's showing at 59 frames per second. And I believe I just saw it go by. So let me go ahead and back up frame by frame. And there it is. Okay. So at around 457, we see that the rubber band enters the field. So from this point, we can see that it's traveled about 1, 2, 3, 4 frames to get from this inch marker to this one. So in 4 frames, it's traveled about 1, 2, 3, 4, 5, 6, 7 inches. Okay. So with that information, we can basically calculate its speed approximately. So to calculate the velocity, we have it's traveled about 7 inches divided by 4 frames, which was shot at a rate of 1/59 seconds. Okay, so that measures it. That clocks it at about 103 inches per second. Now we can convert this to something a little bit more manageable. Let's try and convert this to feet. So it's traveling about 8.6 feet per second. Now, for those who are more used to, like say, miles per hour, we can do this even further. So let's go ahead and first change this to minutes and into an hour, and divide it by 5280, which is the number of feet in a mile. And so this rubber band was traveling not too fast, around 6 miles per hour. Now, this was not the most efficient way to work with this problem. What would happen if we had much more than 1,000 frames, perhaps 10,000 frames? How can we figure out if the rubber band even comes into the field of view at all? This manual approach, while it was very effective at finding it and calculating an approximate velocity pretty quickly, might not work when we have a lot of data to parse through. So let's find an automated way to find the rubber band and calculate its speed. So what I have over here is a MATLAB script that I've already gone through to process some video data. All right, so we can see here, this is the rubber band speed demo. And so what I'm going to do is jump into the rubber band directory that I have here for this particular script. Now, for those who are not familiar with the MATLAB editor, you can see that it's divided up into these cells. And these cells, basically, we can run them independently of all the other ones. And it helps us break up our code into manageable chunks. Chunks that are naturally related to each other. For example, in this cell over here, I'm first going to clean up the workspace and clear out our command window. Okay. Now, in these following cells, we'll see things that we've already touched when we were looking at the rubber band video already. We saw iMac tool. We used mplay to watch the video. And we used these types of calculations. In this case, I was using a different camera when I wrote this script, one that imaged at 150 frames per second. Now, to find an automated way of detecting the rubber band, there are many ways that you can go about this. One thing we can do to take advantage of this situation is we know that the background is not moving. So if we difference neighboring frames, then we'll be left with just the rubber band alone. Okay, so what we'll do is go through some of these functions and look at how this algorithm works. So the first thing we're going to do is use mmReader to read the data. Okay, so the data is now inside MATLAB. If I type whos, we'll see that data is a 4D matrix. Okay. From here, we're going to convert the data into grayscale using the RGB to gray function. And we take the difference. So this is again going back to the concept that the background is not changing. The only thing that's moving is the rubber band. So if we difference neighboring frames, we should be left with just the rubber band itself. From that point, I just take the summation of these matrices, these images, and I plot them. And I'm hoping, when I make this type of plot, that we'll see a spike where the rubber band enters this field of view. And indeed, I can see this spike over here. So this is likely where the rubber band has entered the field of view. We can immediately go to this frame to find our information. So here I'm using a more automated way of figuring out when that rubber band comes into play, comes into the field of view. So here I'm trying to use some statistical approach to detect when the rubber band has entered the field of view. At this point, we have frames that are not changing, just pictures of the background. When it starts to change, over here, when the rubber band enters the field of view, we can basically use a statistical approach to say, at this point, our measurements have gone, say, beyond a standard deviation from the mean. And that's what I do over here. So when it goes beyond the mean, we can detect it and display the rubber band images. So let me go ahead and run this cell, and we can see that I've gone ahead and segmented all the rubber bands as it's gone through the field of view. Again, we have our constant background 1-inch spaced lines. Okay, so with this demo, we've basically seen how we can use GigE Vision cameras and Image Acquisition Toolbox to acquire some image or video data, and then we can use MATLAB and Image Processing Toolbox to essentially find automated ways of detecting when something enters the field of view. So with that, let's go ahead and jump back into the slides and continue onward. Now I want to take a moment and cover who produces GigE Vision cameras. Now, as a reminder, in the previous and in the next demo, we're using a GigE Vision camera provided by Allied Vision Technologies, or AVT. They provide us with one of their GX series cameras. But there are other vendors that are supported with Image Acquisition Toolbox, and I just wanted to list them here for completeness, and so you know which manufacturers are available to work with. So at this time, I think we can go ahead and dive a little deeper into image acquisition and processing. So in this demo, what I'd like to do is detect fingertips when I pass my hand in front of the camera. And so being able to detect fingertips has a few direct applications in a number of areas like human-machine interface, HMI, and also gesture recognition, like sign language recognition. But I think the important part of this demo is actually in its indirect applications, and that has to do more with the underlying tasks that we need to perform when we're looking for these fingertips. How do you detect the correct features and filter out other parts of the hand? How do you segment it from the background? It's this process of feature detection and segmentation that's applicable to so many other different types of problems, like we highlighted at the very beginning of this webinar. So here I've highlighted the 3 main steps that we're going to take inside this demo. First, we're going to acquire some images. Second, we're going to segment it from the background, either by doing some thresholding, perhaps looking at the color information. And third, we're going to start looking at different types of features, using region properties, convex hull, and the curvature of the perimeter. Okay, so here we are back in MATLAB. Just like the previous demo, I've already created a script for us divided into cells so that we can go through them one at a time, and I'll give you a good idea of what the code is doing in each cell. Now we begin by using basically a training set. What I'd like to do is I've already taken some pictures of a hand, and I'd like to practice our algorithms on top of them. And so we can figure out, which algorithms are going to perform the best. So in this cell here, I load in this training set, and I just show them. So let me go ahead and run that. And so this is the image that we'll work with when we start looking at and evaluating which algorithm is going to perform the best for us. Okay. So in this next cell, what I'd like to do is try a number of examples where we attempt to segment the hand from the background. And there's a lot of ways that we can go about doing this. Some are more automated than others. So if we look at the code, I'm actually going to create a figure that has multiple subplots. And in each one, there's a different technique to segment the hand. In the first approach, we use Otsu's method to segment the hand from the background. In the second, we try using a more interactive way to segment it. In the third, we have a manual threshold. And in the fourth, we use the color information to try and pull the hand out from the background. So let me go ahead and run this, and we'll start to see the results in this figure over here. Otsu's method, in this case, didn't do so well, but this is just because we use the default settings. There are other ways that you can modify Otsu's method to perform a lot better. But let's just move on. We could come back to that later on, but let's try some other approaches first. Over here, we see the original image, and this is actually linked to this histogram over here. What this does is anything to the right of this bar is set to white, and anything to the left is set to black. So this is a contrast tool that you can also use to basically interactively find a way to segment a hand, or segment the image. So by making these two bars very close to each other, I can move this up and down and approximate where might be a good point to segment the hand. So it looks like around point 2, it does a very good job of separating the hand from the background. And that's what we see over here in this manual thresholding, where we just take the image and compare it to a single value, and we get the result. Now in this last one, we use a color segmentation approach. And so I've already picked out the colors previously, but basically the way this operates if we take a look at the function, this is a custom function that I put together. I've loaded in some color data that I previously selected and passed it along with this red, the RGB data of this image to this function. So let's go ahead and jump into this and get a better sense of what's going on under the hood. So in this function, I first convert the data from red, green, blue to LAB. And the purpose of doing this is it now represents the image in a luminance channel and two chrominance channels. So it kind of simplifies calculations for us. Because what I'd like to do is take the two colors that I've pre-calculated and calculate a distance from each pixel to this like reference color that I've chosen. And so we can do that as shown over here. We're basically calculating a distance, and we get a metric that says how far away something is. If it's close enough, if the colors are close enough together, let's just set it to 1 and assume that that portion is segmented from the background. And so if I go back to our figure, we see at many points along the hand, it was very similar to the reference color that I chose. Over here is a bit different, maybe because of some shading, but it's done a fairly good job at segmenting the hand. So moving forward, we could use either of these techniques, but I think it'd be very interesting to just use the color segmentation approach, and so moving forward, we'll try and use that algorithm. Okay. So after this cell, after we've basically segmented the hand, we are in a phase of trying out different algorithms to see if we can find the fingertips. And this brings in one of my favorite functions from Image Processing Toolbox, which is called region props. Now, region props can take in a segmented blob and calculate all sorts of statistics about it. If we go to the help, we can get a very good view of what the function can provide for us. If I scroll down, we get this table of all the different types of measurements that we can find. We can calculate the area of this blob, this segmented area, the bounding box, centroid, eccentricity, the perimeter, a lot of different types of statistics that could help us identify or just get a better sense of what this object is. So let's use that in this case. Right over here, I've used region props to find all the different types of measurements, and I plot the bounding box, the centroid, and the convex hole on top of the image. So here's that segmented hand that we had from the lower right of the figure with the subplots. We have our bounding box, the centroid, and the convex hole. And the first thing that catches my eye is this convex hole. At each of the fingertips, there is a slight kink in this green polygon. So we could develop an algorithm to look for these kinks, basically find the angles, and identify fingertips based on those angles. So let's give that a shot. In this next cell, I implement that type of calculation. So here we are doing very similar things. We are taking that hand, finding it using our color segmentation approach, and then I have that convex hole method embedded here in this custom function. Now you might notice why I have a tick and talk around here. In evaluating which algorithm to use, I'd also like to know which one performs the fastest. If we want to use this in some sort of real-time manner, we'd like to find an algorithm that performs well but also quickly. So I'd like to use tick and talk to measure how fast I can segment the hand and find the fingertips. So let's dive into this function and get a better sense of what's going on under the hood here. So just like the previous cell, we use region props to find all sorts of cool statistics about these blobs. I'm finding the convex hole as well as the area. Now in here there's quite a bit of code, but the essence of this is we're going around each of the points in the convex hole and calculating the angle at all of those points. So you'll see in each of these cases, I'm using the law of cosines to calculate the angle. Now there are a couple of special cases, like when you're at the beginning of the polygon and the end of the polygon. These might be where the wrist is or something like that. So we want to handle those carefully and kind of disregard them. But this is really where the bulk of the work happens in this function. It's just using law of cosines to calculate the angle. And down here, this is where we basically look at all the angles and say, if it's within a certain range, we'll consider it a fingertip point. And this can help us take away, the areas where like the wrists are, where the angles may be much smaller. So that is the basics of what is behind this function. So let's go ahead and run this cell and see how it performs. So I'm going to run this and display the results onto a new figure. And so we see it's actually done a fairly good job. It's found all the fingertips here, although we do have one extra one over here by my knuckle. So, we could look at this algorithm in further detail to find some way to get rid of this point, but preserve these ones over here. But let's go ahead and keep what we have right now and try it on some live data. So this is a great way to use Image Acquisition Toolbox to really put this algorithm to the test. We can see how it performs on lots of different data. So what I'm going to do is use Image Acquisition Toolbox. I'm going to access the USB webcam that I have attached to my laptop. And I'm going to start using system objects from Computer Vision System Toolbox. So this is a great product for visualizing video data. As you can see right here, I'm accessing these system objects to not only visualize this video feed that's going to come in from the camera, but also draw shapes on top of it. So I'm going to use the shape inserter to draw circles on where I'm finding these fingertips based off of this convex hull angle calculating algorithm. Okay, so let's go ahead and run this. So it's created our system objects for us. And oh, I forgot to mention the time that it took to run this code here. So for this image, it took about 0.8 seconds to run it. Now with the data over here, with the image acquisition object, we can run it on a smaller frame, so it'll be a lot faster. So let's go ahead and run it right here. This code is going to look very similar. We are segmenting the hand using our color approach. We're using the convex hull method to find our fingertips. And then over here is just the management of those circles that we'd like to draw using Computer Vision System Toolbox. This is kind of managing 20 different fingertip points, depending on what is in the field of view, and then plot them onto the screen. So let me go ahead and run this. And put my hand over here, and we see it's doing a pretty good job. It's finding my fingertips. I can kind of move it around, but when I move my finger inwards, it loses the fingertip, and we can see it's also capturing my wrist a little bit. So while it's running pretty quickly, it's not all that robust. So we have a choice now. We can continue trying to develop this algorithm even further, or we could try a different approach. And so, this algorithm did fairly well, but, MATLAB's great for trying all different types of algorithms, swapping them out to see which one will perform better. So I'd like to try a different approach, and that's what I explore here in this cell, where we use basically the curvature of the perimeter of the hand. Now let me describe this in a little bit more depth by going back to our slides. So we saw the convex hull method where we used basically the green line here to look for the kinks and calculate the angles and then plotted those points onto the image. The curvature approach, I'd like to try a little bit differently by also using some morphological operations. So in this image here, we have our segmented hand. This is done using that color segmentation approach that we looked at earlier in the demo. But what I'd like to do is basically use a morphological operation to kind of erode away the outside of the hand. So it kind of skeletonizes it into this more like pointy segmented area over here. What I can then do is use a corner detector to find all these red points along the side. And I'll treat all of those as candidate points. At each candidate point, I'll then crop out a section of a perimeter of the original segmented hand. So for example, in this red box here, I've taken the perimeter of the original hand and expanded it here in the top right. What I can then do is use region props to calculate the eccentricity of this curve over here. If it's of a certain value, we can say it's closer to the fingertip. At other candidate points, say down here by my knuckle, it's going to be a straight line, and we can tell the difference between these two types. So using this approach, we might be able to distinguish, candidate points at the fingertips versus candidate points, along the finger over here. So let's give this algorithm a shot. I've implemented it here in this find fingertips underscore param function. Again, I have a tick and talk so I can see how fast this thing is performing. We segment the hand, and let's go ahead and dive into here. Okay, so there's a number of functions that I use from Image Processing Toolbox to implement this type of perimeter approach. Okay, so I use the distance transform here to basically erode away the outside of the hand, and I calculate the perimeters of both the original hand and this new eroded version. I can then use the corner function to find all the corner points of what I call the pointy hand, which is again the eroded version of the segmented hand. At this point, I just do some sort of some data management by eliminating candidates that are very close to the border. We'll assume that the hand will be close to the center of the image. Down here, I again use region props to calculate statistics about the areas that I'm cropping away. So if you recall from that image, the slide from PowerPoint, I pull out a small crop portion around a candidate point, and then I calculate some information about it. Oh, sorry about that. Let me go ahead and scroll to the right so you can see what I'm calculating. I'm calculating the area as well as the eccentricity. Okay, so once we've calculated all these different types of statistics for all these candidate zones, we can basically distinguish or try to distinguish the fingertips by looking at the eccentricity and area. So this is the basic approach behind this algorithm. Let's go ahead and jump back here and run it on our training image and see how it performs. And so we see it's done a fairly good job. It caught 4 of the fingers and missed this one over here. But this is likely to be something that we can try to tune for later on. Again, there's a number of different factors that might come into play. How far we're eroding away the hand, how large a area we are cropping around the candidate points, what kind of eccentricity we're looking for. So there's a lot of knobs that we can turn, but already with the kind of the default settings that we've used, it's done a pretty good job at finding the fingertips. Now you might notice over here the elapsed time for this tick and talk took about twice as long. And so this sounds like a very interesting algorithm to take a look at, but if it's too slow, it's not going to be too helpful. So let's try and find the reason why this is taking so long. Now this is a great feature in MATLAB, the MATLAB profiler. What you can do is profile this algorithm that we've just run, and it will show you, which functions are being run, how many times, and for how long. Fingertips underscore param, the function that the algorithm is in, took about 0.9, about 1 second to run. So if I dive down one level, we'll see that region props took up the most amount of time, about 0.7 seconds. One way we can do this is using the Computer Vision System Toolbox. So we've already seen some of the system objects and functions in this system toolbox, particularly the video player, the shape inserter, but there's another one that's like an analog to region props, and that's called blob analysis. Blob analysis does very similar things and calculates statistics about all these segmented objects in your image. And so here we can find, again, the centroid, bounding box, and eccentricity. Here I'm mainly concerned with the eccentricity for the perimeter. So let's go ahead and run this. It'll create our video player, our shape inserter, and this blob analysis block. And we'll go ahead and run this one more time. Immediately we see that the performance version of this perimeter algorithm is running much faster. And if I dive down one level, the blob analysis or region props is no longer at the top level. It's now a different function, which was the second slowest in the previous version. So immediately using Computer Vision System Toolbox, we've found a way to increase the speed of things. So let's try this now against live data. Just like before, we'll use this USB webcam, and we'll set up a case where we will just keep pulling in data. We'll segment the hand, use our function to find the fingertips, and then draw where we detect fingers onto the image. Now something I didn't mention before is this function over here called flush data. Now this is important when we're starting to acquire data from cameras, but also do some sort of processing. This is a very common thing that users will often do. But what happens if this function that we're trying to do, like this perimeter algorithm, takes a long time and it's longer than the frame rate? Well, we can either queue up a lot of frames and we'll kind of lag behind, or we'll need to start dropping frames. And that's what I do over here. With flush data, I'm actually dropping frames that might collect up if the frame rate's very high, but my algorithm can't keep up. So this at least keeps us at the most recent frame. So let me go ahead and run this, and let's take a look at how this performs. Now this looks a little bit different from the last view we had because I'm showing the perimeter, the eroded hand, and the fingertips. And we see it's doing a pretty good job. If I make my hand into a fist, I'm not detecting any points, which the convex version would. If I move my finger in slightly, it still kind of finds my fingertip. And so this is actually performing pretty well. It seems to be pretty robust. So with this demo, we've seen a couple different approaches to find fingertips, using the perimeter method, as well as a convex hole method. And we were able to use the MATLAB profiler to see where we can, improve the performance, and how we can use Image Acquisition Toolbox to basically test out this algorithm and see if we want to continue with it. As a summary, we first began by segmenting the ham. This was a key step. And then we tried using convex holes to identify the fingertips by looking at the vertices of them. But it didn't perform very well in our live data testing. So next we tried using the perimeter of the hand and looking at the curvature to figure out which candidates might perform the best. And those candidates were determined by skeletonizing the hand and looking for corners. Lastly, we used some profiling tools to try and improve the performance of our algorithm. Now, I always like to think about what would be the next steps for our demo. And so I've listed out some potential next steps that we could look at for the fingertip detection. First of all, once we refine the detection portion, I like to look into how we can track these positions. We could use a Kalman filter to input these positions and estimate where the fingertip is going. Now, if we go back to the idea of sign language recognition, a lot of gestures, such as the letter J, which is made by actually sticking out your pinky and making a motion as a letter J, we need to be able to track the previous positions and estimate where it's going in order to identify gestures that require some movement. Second, we can improve the way we segmented the hand from the background. Our background was pretty simple, but in more complex situations, we could use some algorithms such as k-means clustering, which is a statistical approach to it. Lastly, we could optimize the algorithm even further, convert it to fixed point, and generate some C code from it. That would help us embed the algorithm to a system like a DSP. Now, demos for all these next steps are available in MathWorks products, although they may work with some different scenarios, but the core idea is there. So if you're interested in these kind of next steps, I invite you to take a look at it. You can log on to our website for more information or play with the code in MATLAB itself. Now, one of the next steps I mentioned was embedding an algorithm to hardware, like a DSP. And so I'd like to revisit Computer Vision System Toolbox, as it gives us features and functionality in this space. Now, as a reminder, we use Computer Vision System Toolbox in the fingertip demo to help us visualize streaming video, draw markers onto the stream, and also with blob analysis. So it helped us speed up our algorithm. Now, the System Toolbox gives us many more functions and system objects, particularly in computer vision. For example, it can help us estimate motion and track objects and perform stereo vision. I've listed a few algorithms here that might help us in that area. But it also gives us features in converting an algorithm to fixed point, which is necessary to go to, say, like a DSP or an FPGA. And it also helps us automatically generate code, which is really important when you want to rapidly, develop an algorithm and try out new code without having to keep rewriting it. We've taken a good look at what the products can do and how we can use them in some demos. For now, I'd like to take a moment to cover the breadth of what Image Acquisition Toolbox supports. Now, our conversation has been oriented around GigE Vision cameras for now, but the nice thing about the product is that it's set up so that you can change cameras depending on your needs. So the code we saw today could easily be modified to work with FireWire cameras or CameraLink cameras, for example. Now, I've listed some of the types of camera interfaces that the toolbox supports. In addition to GigE Vision, we support a number of frame grabbers for analog and CameraLink cameras. CameraLink is often used for very high-speed image acquisition, which could be useful in problems like the rubber band demo when you want to look at higher velocity objects. Now, I've also seen a variety of non-visible cameras like infrared cameras with interfaces to analog and GigE Vision. So the toolbox supports those kind of cameras as well. We also support DCAM FireWire and common OS webcam interfaces like Video for Windows, Video for Linux 2, and QuickTime. And so with those, we're able to provide support for other operating systems like Windows, Linux, and Macintosh. And if you're interested in finding out more about what cameras are supported, I'd recommend checking out the supported hardware pages available on our product page for Image Acquisition Toolbox. You'll be able to find the most up-to-date information there. And so with this list, we're able to see that the toolbox is generally more focused on supporting industry standards. And through these, we're able to provide access to a large number of manufacturers. And I've listed some of them here. We have Allied Vision Technologies, as we saw in the demo, but I also wanted to list out some of the other manufacturers that are available. Again, if you're looking for a particular manufacturer and you don't see it on this list, please check out our supported hardware pages. If you don't find it there, there's also a request area where you can request for support for a particular type of camera vendor. Now, through these industry standards, the toolbox supports commonly used camera properties and features, but there are often proprietary properties that the vendors would like to expose to users. The toolbox is built to be extensible through what we call adapters. It's a layer between Image Acquisition Toolbox and a camera vendor's SDK. So for example, Allied Vision Technologies has created an adapter for their FireWire and GigE Vision cameras. It gives access to various vendor-specific properties, and recently it provides support for link aggregation. Now, this is a feature that lets you use hardware like dual-port Ethernet cards, and is a great way to boost the throughput and increase frame rates. So if you're interested in working with their adapter, you can find it on the Allied Vision Technologies website, but it's also linked from our supported hardware pages as well. If you're looking for an adapter from a different vendor, it may be available on our website as well. Go ahead and check it out, and if you can't find it, send us a message and we'll contact the vendor to see if one's available. So with that, I'd like to summarize some of the key points from the webinar. With the Image Acquisition Toolbox, we saw that we could easily access cameras and frame grabbers and pull data directly into MATLAB. As we found in our fingertip detection demo, doing so makes it really convenient to test out our image processing algorithms and see how robust they are. It also enables you to automate the acquisition process, so it's easier to test a lot of data. The toolbox also provides support for many industry standards, enabling connectivity to several manufacturers, and the toolbox can be extended using these vendor-specific adapters, so it provides even more access to camera features. Now from our demos, we also saw that MATLAB is a great place for image processing. Using some high-speed imagery, we were able to record and post-process the data to calculate the speed of a flying rubber band. We also tried various fingertip detection algorithms and tested them out against various scenarios to see how well they performed. The ability to flesh out where an algorithm is failing and to quickly try some new image processing algorithms really cut down on the development time. And furthermore, the bottlenecks could be identified using profiling tools, and in future iterations of our algorithm, we could deploy it to other PCs or embed it to hardware. Now, something we didn't get to cover today, but I did want to give you some idea, is if you're working with large amounts of data, you can make use of a product called Parallel Computing Toolbox. This toolbox lets you use parallel computing clusters and multiple cores in your machine to basically divide up an image processing job and execute it faster. So you're leveraging more hardware to increase your computing power. Now, unfortunately, we didn't have enough time to go through that, but there's a large amount of information available. And so I mentioned several times throughout the webinar that there's a lot of other places to get information, and so I've collected some of them here. I've put together some titles and some demos that could be useful, as well as some webinars that are recorded and available. So please feel free to check them out and watch them at your leisure. They're great for learning how to use the tools and to get some ideas for various image processing problems. For me, I feel the fastest way to learn about a product is really to just play with some code. So you can access several of these demos through MATLAB, but also view web-based versions of them on our product pages. Now, if you have any further questions that you'd like some more support on, please feel free to contact your sales representative. They can get you in touch with an application engineer, and we can have further conversations about how you can do image acquisition and processing. With that, we've come to the end of our webinar. So again, thank you for your time. I hope you found the webinar both educational and entertaining. So, thanks so much and have a great day.